everybody. You can grab a seat. Welcome. I'm Pat Jenny. I'm president of the Salisbury Forum, and on behalf of the board, I welcome all of you here tonight to Housatonic Valley Regional High School. And we are very excited for our program this evening with Dr. James Shepard. As you all know, our programs are free to the public, and we count on your support and are very grateful for your ongoing contributions. In this giving season, we're going to ask for your donations, and we're going to try to make it very easy. You can go to our website, salisburyforum.org, hit the donate button, and pay either through PayPal or Stripe with your credit card, or send us a check or give us a check this evening. We have very little overhead because we do not have a staff, so most of your donations go right to what we'll be putting on the programs for 2024. Speaking of which, our first program in the new year will be on a Thursday, February 8th. It will be a Zoom meeting, a Zoom presentation with Bonnie Glaser, who is from the German Marshall Fund now, GMF, and she's on a return visit to the Salisbury Forum to speak about our ever-changing relationship with China. And as noted in the program that you have this evening, we will continue to explore the very broad theme of geopolitical issues in 2024. On March 8th, we have authors Andrew Hone of the Rand Corporation and Tom Schenker, formerly a journalist with the New York Times, to discuss how to keep America safe from various threats, including cybersecurity and climate change. And then on April 5th, we will have Richard Haas, who is the very recent past president for 20 years of the Council on Foreign Relations. He was also a former diplomat, and he has a new book called The Bill of Obligations, which identifies how American citizens can get involved in very practical and peaceful ways with various issues. So this evening, we have a focus on public health. A rapidly warming climate not only generates dangerous weather events, but certainly heightens the risk of infectious diseases, including ticks and mosquito-borne illnesses like Lyme, which all of us are familiar with in this part of the world, or dengue fever, or infections carried by water or food. Our experience in the past couple of years with the global COVID pandemic has given us a taste, perhaps, of our public health future. This evening, we welcome Dr. James Shepard, who will help us sort out how we can manage this frightening prospect. So Dr. Shepard is currently Associate Professor of Internal Medicine in Infectious Diseases and on the faculty of the medical school and the Institute for Global Health at Yale University. For 9 years overseas, he advised the government of India on tuberculosis control and prevention he also directed a research program on tuberculosis, TB, and HIV for the Centers for Disease Control and Prevention in Botswana. And he assisted the University of Maryland with a large AIDS treatment program in Nigeria. In 2014, he and his family returned to the US. His wife is Shrivi, who's here with us this evening and is a former board member of the Salisbury Forum. They purchased an old 175-acre dairy farm in Sharon, Connecticut, and they decided to grow hops on 9 acres of that farm. Apparently, it's a very complicated crop to grow, but now their farm is providing hops to some 30 local brewers for beer. Along with his farm, Dr. Shepard continues his stellar career at the Yale School of Medicine. He sees patients and he teaches medical students. He also continues to consult with global organizations like the World Health Organization on COVID and other infectious diseases. And as you will note from his accent, Dr. Shepherd hails from England, where he got a PhD from the University of London before moving to the States, where he graduated from the Columbia University College of Physicians and Surgeons, completed his residency in internal medicine at Beth Israel Deaconess Medical Center in Boston, as well as a fellowship on infectious diseases at Johns Hopkins. So please join me in welcoming Dr. Shepherd to Salisbury.
Well, thank you, Pat, and thank you for your generous welcome. I want to get started. You're the recipients of a lecture that I gave this week on Tuesday to the incoming Yale School of Medicine first year class, who are obviously very bright, very engaged and interested, and also non-expert. They're at the beginning of their medical careers. So I'm hoping what I developed for them and taught earlier this week will work for a similar audience, if not slightly older, if I may say, today. So it is me. I, as you can see, have a beard now. And this was my penance during COVID. The hospital, Yale New Haven Hospital, said I should shave because the N95 masks didn't properly fit to my face and provide any protection. And as soon as your workplace asks you to do something, at least my response is to refuse immediately. And so their comeback was to make me wear a positive air pressure respirator, which had a tube in the back and a power pack clipped to my belt, and you don't see all of the coverage that was over the top of my clothing at the same time, and a surgical mask, and inside this little dome was a jet of air that came through the back and flowed down over my head and then out through some air holes that you can't see at the bottom of the mask here. And so back in March 2020, when we first started to deal with the surge of COVID here in Connecticut, and particularly at Yale New Haven, I would get all gowned up and put on my helmet and connect the battery pack and have the air starting to rush over my head and go into an airborne isolation room to see some poor patient who had gotten infected with COVID and needed to be admitted and was now really terrified, in complete isolation. And I would walk into the room, and the first thing that would happen was that the visor would start to fog up with the condensation. And I couldn't hear a thing because of the air rushing down over my ears. And I was dressed in a sort of big puffy blue and yellow outbreak suit, and would begin gesticulating with my rubber gloved hands at this poor person. So it was really much less than a productive time. And really, at the very beginning was, as I'm sure many of us can remember, quite shocking. The beginning of the lockdown, I was one of the only cars on the road coming from up here in the northwest corner and driving down to New Haven. So there's the context. This is the first little story I've told you and going to tell you about, which was just 3 years ago. And then I'm going to tell you about another story about a pandemic 100 years ago in the next couple of slides. And it's probably not the epidemic that you think I'm going to tell you about. but I think it's one that illustrates the general talk that then I'm going to give, which is what I highlighted for the Yale medical student class. So let me tell you two stories of two pandemics, one recently and one about 100 years ago. So the one, and this is a slide from before SARS was called, COVID was called COVID. It was the 2019 novel coronavirus. And I just want to illustrate here that the timeline really was quite remarkable. The virus began to spread in Wuhan probably around late November, early December of 2019. And the WHO was informed by the Chinese government before the end of the year, December 31st, 2019. I can remember SARS-1 back in 2002, 2003, that we also dealt with at Johns Hopkins Hospital where I was practicing then. And it took months and months for the communication to take place. So this was remarkably quick. But then I want to highlight that on January the 7th, just a week later, the full sequence of the offending agent, the actual virus that causes COVID, was already published and available. In fact, 7 full-length sequences of the virus had been isolated and shared completely. And the first tests were available about 2 days later. Anyone could have tested for COVID at that time. It was already posted by the WHO internationally. So we, unfortunately, were blind at this point because we couldn't use those tests. The FDA would not approve them. But the point is that this epidemic, the information sharing and the timeline for identification of the pathogen and the testing availability was quite remarkable for most of the world. Unfortunately, not for us at Yale New Haven, where we couldn't do testing. And then we knew very quickly by the mid-January that this was going to be a huge challenge. An asymptomatic virus that's able to spread prior to the emergence of symptoms, human-to-human transmission. And I think that really the rest is history. My wife and I were traveling in Botswana in February the 2nd of 2020. And the plane that we took from Johannesburg up to Gaborone, the capital of Botswana, was full of Chinese people returning from the New Year in China. And the Wuhan lockdown, which actually occurred on January the 23rd, 2020, approximately 400,000 people had already traveled out of Wuhan International Airport and the train stations and spread across the globe. So I think that it's very clear that even with the speed at which you can see things actually were identified, testing became available, the speed at which our world travels and people move, I'm not sure that we really could or can do any better when the next one comes along. I'm just going to put these up quickly to just point out that although the response to the pandemic has become highly politicized, and I don't want you to read this, I probably shouldn't have put it up yet, but don't read it. These were our instructions on how to treat COVID from our pharmacy committee at Yale New Haven Hospital that's very active. And we did a lot of things very early on, if you look down at March the 17th, 2020, that we wouldn't be particularly proud of in September 2020. And one of the things that we used greatly was hydroxychloroquine, which obviously developed quite an association with political affiliation and didn't work, but we thought it might. This is an HIV protease inhibitor, which was quite fanciful. We should probably never have used it, and we caused some problems with it. And by September 2020, we were actually using probably the single most important treatment that was developed throughout the early phase of the pandemic. And this was created from data in another healthcare system, the National Health Service in the United Kingdom, where I originally come from. Another point about this most recent pandemic I'd like to just put out there, nearly all of the good data that we developed for best standard of care came from the NHS and the WHO. And the United States healthcare system provided almost none of the useful standard of care treatment data. I'll leave you to make your own conclusions, but it's largely because of the broken up nature, the business model, the small scale health networks that don't communicate with each other, and the inability to do large scale, real time trials of different treatments that failed us. And we used the data from outside. At about the same time, I'm going to show you a little photo album as ex-WHO, and unfortunately with our administration's decision to leave the WHO around this time, I was asked to come back in as a personal consultant and run the clinical response to COVID in what is probably the world's biggest refugee camp in southeastern Bangladesh, in South Asia on the Bay of Bengal. You can see Myanmar here, and it's essentially all of the Rohingya Muslim people that were expelled from Myanmar as an operation of ethnic cleansing. And of course, a COVID epidemic in 1 million person refugee camp is obviously a serious business. And we did our best. We mainly constructed a healthcare network made of bamboo and built oxygen generators and essentially just put together what was a health network run by partners within the camps, training. You can see the drainage system was not very good. And we transferred the experience from Yale direct to Cox's Bazar via the internet. We did remote training, management. We essentially found resources. We discussed cases. We were linked to the intensive care unit in the local town right next to the refugee camp. And we consulted online, and it was quite a strange experience to be sitting in Sharon in the snow, for instance, of the winter of 2020, listening to the tropical birds and the muezzin call to prayer in the evening as we were doing case rounds over the computer. And I highlight again that one of the great successes of the pandemic response was the high quality data from the UK National Health Service and the WHO trials that were run that essentially established a standard of care for COVID, which was a steroid that they studied that was freely available everywhere. And we basically used this because we knew that they could use it in Bangladesh as well as New Haven, Connecticut. And proning, flipping people on their stomachs to ventilate them, proved to be the other major impactful treatment that we could bring pretty much everywhere. So now I'm going to go back 100 years and talk about another pandemic that we're still living with, that you may have thought I was going to refer to the 1918 Spanish flu pandemic. But I think in many ways the HIV pandemic is more instructive about what our future is going to look like. So here's a question I ask the students, and usually someone at the back steals my thunder and says about 1,000 times did HIV jump from primates into humans, but it actually jumped probably at least 12 times within the last 120, 140 years. So the epidemic that we see today, the global HIV pandemic, is caused by what's called Group M HIV, HIV-M. But there's N, O, and P. There's an HIV-2 that came from another monkey into humans. There is HIV from lowland gorillas that made the jump from gorillas into probably a bushmeat hunter somewhere in West Africa. And so we have evidence of at least 12 of these spillover events for HIV-type viruses, HIV-1 and HIV-2. So my point here is to point out that these are common events. Coronaviruses are the same. In fact, there's still evidence popping up at the moment about new coronaviruses jumping into people. There was an example in Sarawak on the island of Borneo. So these things happen all the time. And so in the next slide, I'm going to sort of lead us through the story of how HIV became a pandemic. Basically, the HIV-M subgroup probably jumped from a primate, a chimpanzee, into a hunter, maybe a bushmeat hunter, butchering up a chimpanzee in southeastern Cameroon, estimated somewhere about 100 years ago, maybe a little more than that. And then made it to Kinshasa, probably down the Sangha River, which runs down and joins the Congo River, through trade or migration. And really the event that made HIV a pandemic, because this was happening all the time, this spillover, was the development of Kinshasa by the colonial authorities, the Belgians who owned Congo at that time, into a major trade and transportation hub. And an accumulation of young men in Kinshasa who were brought in to work in the various industries, transportation, trade, and HIV began to spread within Kinshasa. And the earliest virus isolated that made all of this molecular history of tracing HIV through West Africa, the earliest virus was isolated from 1959, a small sample from a patient in Kinshasa. And then it already was traveling up the river, down the railway line to the big copper mines in northern Zambia, through Lubumbashi, up into the forests and eastwards into East Africa along the trade routes, and down to the major port, Pointe-Noire, where likely it was introduced into Haiti, where there were a lot of teachers teaching in Pointe-Noire. And so HIV-1 subtype M has caused a global pandemic that we're still dealing with. And the main factor was the development of Kinshasa as a trade hub and an interconnected network. So this is the lecture I gave earlier this week that I alluded to. So I'm going to sort of switch a little bit over from the history, the story of COVID, the story of HIV, and talk about some of the factors that I was talking with the students about that promoted the spread of those two pandemics. And I want to highlight that the three major factors that I'm going to be talking about are global warming. I prefer to say that than climate change, because it's actually what's happening, and climate change sounds like such a sort of neutral phrase that I'd like us to focus on actually what's happening. Urbanization and biodiversity loss as three prime factors that are promoting this movement of viruses and could be related back to HIV and could be related into the future to the next pandemic. And as I talk about these things, I want you to just keep this classic structure in your minds. This is what introductory classes to epidemiology talk about as the epidemiological triangle, where an interaction of the environment, a host, in this case us, and an agent, in this case an infectious agent, interact with each other in such a way that the host and the infection are efficiently brought together. And so when I talk about the different factors, think about the different three inputs into any epidemic equation can be used. And it's an interesting time to be talking about it, because yesterday COP28 kicked off in Dubai, and the discussions continue from a series of missed targets from all of the previous COPs at this point. And at this point, it certainly looks like we will not meet the goal of avoiding a global temperature rise of above 1.5 degrees centigrade. So things are moving increasingly quickly, and the planet is heating much faster than we expected it to, and continues to do so unless COP28 is more successful than it looks like. And this is an old map from Klein. It's kind of a famous one that shows where the initial effects of climate change will be most significantly felt, of global warming. And if you look, you can see in the red, this is the biggest losses in agricultural productivity by 2080. And there's a lot of other projections out now, but they all pretty much look the same. That the global south, but even the southeastern United States, South Asia, Africa, northern South America, Australia, are going to suffer the effects of the warming climate first. And this process of climate change, of agricultural productivity decline, of the impacts of warming on traditional rural life is fueling a massive migration of humans. This is possibly the most significant epidemic or pandemic factor that is going into our future, urbanization. And let me just explain this graph. If you look at this is a UN graph from a couple of years ago. The size of the dots are the size of current cities, but I want you to focus on the dark color of the dots. which is the rate of population growth in those cities. So the fastest growing cities are through Central Africa, South Asia, East Asia, and Southeast Asia. So in those same overlapping zones of the loss of agricultural productivity and the most earliest impacted places on Earth through climate change. So these places are urbanizing incredibly quickly. Just to highlight and emphasize what this means, if you look here at population growth, we've based most of our projections of population growth on UN data that currently estimates that we'll peak at about 10.5 billion people by 2080. But there's a lot of other models starting to question whether that's really the case. And I'm just highlighting one here. This was the University of Washington group that you may be familiar with from COVID that produced a lot of the modeling for projections of COVID, that we may peak humanity may be reached in the middle of the century, so less than a generation from now, and only 10% or even a little bit less than the total number of people that already exist. And so the total population growth seems to be no longer a major factor, but what is urbanization increasing the population density. And you can see that the UN projection is that we will increase our density by 50%. And this is obviously the principal metric for the risk of epidemics and pandemics, how many of us are packed in, how closely together. And I just want to point out that today, the biggest cities in the world, the top 4, are in Asia. By the end of the century, the biggest cities, and here's our old friend Kinshasa, Lagos, Dar es Salaam, are in Africa, right in that same belt of impacts of climate change, declines in agricultural productivity, and in rapid urbanization. And for pandemics, that's fuel to the fire. I point out some real data. This is a slum, it's called a slum by the Indians, so I'm not being pejorative, called Dharavi, which is a very famous slum. It's in Mumbai, right in downtown Mumbai. And for TB doctors like me, this is a place that a lot of the research has been done. This is where we first isolated totally drug-resistant TB, which is TB that no longer has susceptibility to any antibiotics. So it's an exceptionally densely populated place of 350,000 people per square kilometer. From the beginning of the COVID pandemic to 4 months later, essentially 2/3 of Dharavi became infected with SARS-CoV-2. So this is the future of the host, us, in densely packed communities, mostly like this. So this is where most of the population growth is going. Poorly serviced communities of migrants coming in from the rural areas, joining family, moving into tin huts or constructed, no sewer, no water supply, no electricity. And that's where the majority of those big growth numbers that I showed you. So urbanization is number one factor. I just wanted to put this in because thinking of our epidemiologic triangle and some host factors, as well as some biodiversity factors, pollution is one of the major global events that is continuing to drive biodiversity challenges. And this is a young man called Forby Parise, who lives in coastal Cameroon, in English-speaking Cameroon, who's taken it upon himself to clean up his town. And you can see, and if you've traveled in Africa or Asia, this will not be unfamiliar to you, the discarding of plastic in the environment everywhere. Almost all the plastic that's ever been made is still in existence, and it ends up like this. In fact, it ends up as microplastics. And it's estimated that us humans consume about a credit card-sized amount of plastic every week in our diets as microplastics, which largely ends up in our immune systems. Macrophages gobble it up, take it into our lymph nodes, and it sort of sits there because it's not going anywhere. And so it almost certainly has an impact on our health and immunity. This is air pollution. This is New Delhi, India Gate. You can just about see in the haze. This is an annual event now. In fact, they're right in the middle of it. This is the pollution time in Delhi. The estimates were that children probably gained life years during COVID at the beginning in India because of the lockdown. There were no cars and the pollution was significantly better. So these are host factors that affect us and our ability to resist and survive infections. Talking about biodiversity, this is like the stepchild COP. COP15, you probably, some of you I hope remember, was supposed to take place at the beginning of the pandemic, where a lot of spillover occurs in Asia, in southern China, in Kunming, and couldn't take place because of the lockdown. Did eventually happen late last year in Montreal. Unfortunately, we don't even have a home for the next biodiversity COP because Turkey cancelled, understandably, because of the earthquake. So it's homeless at the moment, and in many ways as important as the COP28, the global warming COP, because this is another major factor in our pandemic risk. Of course, we have not ratified the Convention on Biodiversity. Congress has failed to ratify it. I think we're in the company of Andorra and Somalia at this point as the only countries globally that have not ratified the Convention on Biodiversity. And we've missed the targets again. The basic enforceable, or hopefully enforceable, goals of the Convention on Biodiversity is to improve biodiversity by decreasing pesticides, plastic pollution, and the famous 30 by 30, protect 30% of the land by 2030. I think we probably suspect that isn't going to happen. And why is that important for infections? This is a study that there's quite a few ecosystem studies about global warming and biodiversity loss. I quite like this one, where a couple of scientists associated with the Rensselaer Polytechnic Institute measured the temperature in the canopy of the Puerto Rican rainforest, which, as you can see, since 1979 has been steadily going up, and linked that to drops in insects. Back in 79 and 77, there were lots of insects in the rainforests in Luquillo in Puerto Rico. All the follow-up studies, 2013, I think, I can't quite read that, it's a bit hazy, have shown precipitous drops. And this is repeated everywhere. All of the studies show these losses of about 3/4 of insects. And these are losses of animals that depend upon insects, lizards and birds, which we're also seeing everywhere. So biodiversity is really in decline. As I sat in my office on the Zoom calls with Bangladesh, listening to case conferences about COVID patients in the Sadar Hospital ICU, I could look out of my window into the Connecticut forest and see a recent, I'm calling it a pandemic. Many of you have seen this bark from emerald ash borer, which is invasive, another major factor in biodiversity losses. That is moving through our woods, may well kill, and may not. I would defer to the foresters in the audience. But in contrast to COVID, which killed a relatively tiny proportion of humanity, tragically, but nevertheless a tiny proportion, this little fellow will potentially kill every single member of the ash species. And just to highlight, ash is home, an essential home to all these other species, estimated at least 43 insects known to completely depend upon ash. And then the subsequent links between those insects and other animals in the forests. And they are gone. Here's a tick, which will become relevant shortly. More bad news. It seems that every beech in our forests is going to be killed by this brand new nematode called beech leaf disease, Litolencus nematode, which causes these striations in the leaf. Looks like potential mortality also of 100%, a climax species of North American hardwoods. Many, many other species that we don't even know are completely dependent upon it. And so why is that important for infectious diseases? Why am I telling you about trees instead of people and fevers? And because of an effect, a disease ecology effect called the dilution effect. And I'm using this Lyme disease model to illustrate it. When biodiversity is high, which means a lot of native species living in their niches in a healthy, unperturbed ecosystem, then a reservoir species, or potentially a vector species, so either the tick or in this case the deer mice, have their niche and have to compete to exist and will be maintained at a certain level due to natural competition within that healthy ecosystem. When biodiversity falls, and in this case they've indicated agriculture might be responsible over here, pesticide use, say, or clearance of habitat, then a reservoir species tends to do better than any other species. Rodents breed rapidly, they're not as affected by the pathogens that they carry, in this case Lyme, as these other species, and so they proliferate. And so reservoirs of infections increase. And the vectors themselves that depend upon those species also proliferate, and the disease that they transmit goes up. So to continue using Lyme as an example, this is data from NASA, which I'm glad does this. They actually do lots of excellent climate change data. This is Lyme. This is the deer tick that transmits Lyme. And its distribution here in Connecticut, as you can see down here, this is 2000. This is the distribution of the deer tick in Connecticut 23 years ago. This is 2015. The rate of movement of this vector is quite stunning. And I can tell you in Ontario, they had, I think, 8 cases of Lyme disease in 2000. This year, with 2020, which was the last year of data of Lyme in Ontario, they had well over 3,000. So these things are happening so shockingly quickly. These vectors are moving northwards with the increasing temperature and the declining biodiversity. Another vector Aedes mosquitoes, which transmit Zika, dengue fever, chikungunya, some other what we call arboviruses, are also moving northwards. This is Aedes albopictus, which is kind of like a woodland Aedes, but can transmit all of those infections. We're in an unusual situation right here in Connecticut because we've been right on the kind of breeding edge, but we have breeding populations now of albopictus mosquitoes. So it has become an endemic mosquito in our area. More good news. This is from just before the pandemic. This is our state not ecologist, I'm having a brain, Gus Malay guy, anyway, in the New England Journal of Medicine, measuring the Texas Lone Star tick, which is a southern United States tick, has moved up our coastline and is now actually beyond this. The last couple of years, breeding populations in New London County, New Haven County, as well as Fairfield. So it's an endemic tick vector, a new endemic tick vector to add to the deer tick is now established as a result of warming and of biodiversity decrease. More good news? So the deer tick for Lyme, the Lone Star tick, we just looked at the map. Longhorn tick is also established in southern Connecticut. Another new tick vector, Gulf Coast tick, is also now established in southern Connecticut. And only a matter of time with warming winters and habitat destruction, things like ash trees dying and their natural tick competitors dying off in the wild, these ticks will move northwards. So why is that important to us in this room? Well, this is a kind of a standard patient. Let's say the Sharon Hospital emergency room in the summertime, a local resident comes in and has a fever, headache, muscle aches, abdominal pain, and nausea. Probably familiar to pretty much everybody in this room. Very common presentation, particularly in the summertime, but at any time of year. And some blood tests, and I won't go through them because I'm running on a bit, that are largely uninformative. They often look like this. And despite all the treatment that we give, which is all pretty standard treatment for this presentation, the patient gets worse and all of the diagnostic tests are negative. So because of these expansions of vectors that are moving into our area, bypassing us and heading north and west, in 2010, this was really the differential for that presentation. There really wasn't anything else in a local person that we would consider, and Lyme, Babesia, Ehrlichia were all fairly common. Enterovirus, could have picked it up from one of their kids. That would be the differential. West Nile, another new invasive infection, possibly. In 2027, and the reason I put that up there at that date was because that's the graduation year of the class that I just talked to. And so they are going to have to actually lengthen their differential diagnostic lists to practice if they stay around here. These ticks, the Aedes mosquitoes, transmit a much wider variety of infectious diseases. So sitting here in your garden in Salisbury or Sharon or Cornwall, you could get infected with Heartland virus. Anyone know what that is? I'm not sure either. But there was a case in Maryland this year furthest north, and it's moving in our direction, and it's transmitted by the Lone Star tick. And it was a fatal case in Maryland. Severe fever with thrombocytopenia virus, very common actually in China, Japan, East Asia. In fact, very severe. It has a mortality rate of about 30%. It's just been renamed Dabi-Bunya virus. And it is transmitted by the longhorn tick, which is here. We now have longhorn tick vectors living, if you live in southern Connecticut, living amongst us. And so all we need is a host, a person coming here with severe fever with thrombocytopenia virus and the tick, and sooner or later there will be transmission. Rickettsia parkeri, this is Rocky Mountain spotted fever. Rickettsia parkeri is a slightly milder version. It is transmitted by 2 out of those 4 new tick vector species. Tick-borne encephalitis, quite common in Europe, also transmitted by those species. So this is southern tick-associated rash illness. Anyone want to get that? I don't think I do. Really, this is meat allergy, which some of you may have heard about, also transmitted by these new tick species. So my point to the medical students was, in short order, really within the career of all of us, their short education, things will have changed as a result of our environment changing very rapidly around us. So here's my plug for my neighbor who is on Sharon Mountain and has Michelle Alfandari, who's sitting down there, with Doug Tallamy, who I'm sure many of you went to his talk over at the Carey Institute a couple of weeks ago, which was much nicer than my talk. He talks better than me, and the pictures of his caterpillars are much lovelier than the viruses and worms that I've showed you. So Michelle and Doug started an organization called Homegrown National Park, because I feel that looking at COP28 or COP15 and our political inability and the way our globe is set up, that urbanization and human migration into the cities is such a vast and feels like an unmanageable situation without much better global cooperation and a complete change in the way that we deal with things as international communities. So how about doing something in your own backyard? And the organization, Homegrown National Park, recognizes that most of the United States, for instance, is in our own hands. It's private property. We own 4/5 of it. And so you can do this without despairing of your politicians or your COP28 deliberations. And you can set aside some of your property for biodiversity, for native species that will support other native species. And I hope now that you have a link between the risk of infectious disease and vector expansion and movement of new pathogens into new areas and the loss of biodiversity and the fact that you can restore the biodiversity on your own plot and provide some resilience to our systems, to the world in which we live, that you will go on homegrownnationalpark.org and get on the map. You can put your property on a map of the United States and begin to restore some resilience and biodiversity, and we can democratically do our own bit to lessen the expansion of things that are going to make our lives a little more challenging. I'm going to leave you with a couple of quotes, one from a little while ago, one from today. The old one, it's not that old, E.O. Wilson, who died, I think, last year, the famous founder or theoretician of sociobiology, the Harvard ecologist, who says the point is that human nature has not changed enough. Our strongest propensities of a social nature tend to disfavor the lives of most other species. And we have to change. We have to recognize something that, and I don't usually quote English monarchs, King Charles III said today, and frankly I think he gave the best speech at COP28 that I've heard, the earth does not belong to us, we belong to the earth, which is a small mark of progress, because King Charles I was beheaded for insisting on his divine right to rule. So we've definitely made some progress. Thank you.
Hello, I wanted to take a second to recognize today is World AIDS Day, and I thought maybe you could just take a second or two, maybe to end on a happy note, and talk about where we are with HIV and AIDS.
Thank you. As an HIV physician and practitioner in New Haven, I take care of a lot of people with HIV infection. And I think that although it has been the pandemic of my career and continues, still in many communities, so certainly the appearance that it's gone is not true at all. I think that the great success, and I pointed out what I thought was the great success of the COVID pandemic, which was much better treatment that we learned how to deliver. HIV has become a manageable disease for people that can access care and receive the treatment. And it is one of the great successes of modern medicine. In fact, antiretroviral therapy is as amazing as penicillin in transforming the course of an infection from almost universally fatal infection to becoming a chronic condition that can be managed for a lifetime. So we can do good stuff, and we continue to do good stuff with HIV, and I do hope that that will continue.
Hello, Catherine Palmer-Payton, doing a little bit of permaculture, which I hope is a familiar word for a lot of people. Have you heard of it? And I have a game I made because I took a class to try to teach people about that. And what can we do as communicators to just share a little at a time? Because most of the world's not tuning into this on a grassroots level. Do you have some ideas there? Or maybe we can all network, but colleges and social media like clubhouse.com, which is people talking all over the world. If we could have kind of a curriculum we could all put into practice. It's a little bit like the national park idea, homegrown. You could maybe speak to that a little, if there's some, with activism from Audubon or the Greenpeace and things, is somebody putting it all together so every citizen could start sharing the ideas?
Well, I may not be the right person to answer that question because I'm a doctor and an infectious disease specialist, not an ecologist or an agriculturalist or even a community activist. And it's why something like Homegrown National Park struck me as so valuable, because of the democratic nature, the grassroots level that I think that you're involved in with permaculture. I'm a follower. I would join in for sure and add my voice, if it's worth it, to any discussion about making our environment more resilient and more able to withstand the rapid changes that are occurring around us already and will continue to. But I applaud your efforts, and if you need an infectious disease doctor, I see patients.
Thank you for doing this, and before I get too depressed, can you tell us some hopeful news of how your research and other research is keeping one step ahead of all this, so that it's not as grim as you pointed out?
Well, I think the grimness is lent from the fact that I think we still consider ourselves the exceptional species, and that it's happening to us. And these are natural processes, and I'm not sure I can reassure you, Phil, very much that the next pandemic isn't already on its way. And if it doesn't come before I retire, and you can see that that probably should come sooner rather than later, I would be surprised. I think that we, as I pointed out, in 100 years, our ability to identify and begin to develop treatments and testing and a vaccine for COVID was remarkable. I mean, we did it in a few months, initially in a few weeks. And, you know, despite the inequitable world and the uneven distribution of resources and healthcare, we still tried to make available all of the things that we discovered to everybody, which wouldn't necessarily have been the case 100 years ago. So I think there's progress, so don't get me wrong. But with 8.5 billion of us, highly densely packed in highly interconnected urban centers, largely spread across a world that is heated up and is as disrupted and losing biodiversity at an intense rate, I think you can see that what we're doing is creating a very effective disease amplification system, and we have to be ready to deal with that.
Could you just tell us a little more about the origin of, a little more about viruses themselves? What, are they single-cell organisms? Are they multi-cell organisms? How do they develop transmission, vectored, their methodologies, anything like that?
Yes. Well, first of all, let me point out that viruses aren't the only infections.
Yeah.
There are bacteria, there are protozoans like malaria or babesia, and there are worms or flies or maggots or big things. Viruses tend to be pandemic causes because they are reproduction machines. What they are very, very tiny little pieces of nucleic acid. HIV, for instance, is 10,000 base pairs. Just for reference, in us, we have a 3 million base pair genome. The average bacteria may have a couple of thousand to a couple of 100,000 base pairs. So this is tiny, tiny sliver of information that contains only maybe 20, coronavirus, SARS-CoV-2 that causes COVID, has 25 genes. We have hundreds of thousands of genes. So they're stripped down reproduction machines. And what they do is reproduce. And HIV, for instance, reproduces with such a shoddy reproduction mechanism. It's kind of a junky machine that doesn't work entirely properly. But for HIV, that causes a new variant to occur every reproduction cycle, because it incorporates lots of errors every time it copies that little sliver of nucleic acid. And so what happens in viral infections, COVID was the same, every day you would get every conceivable permutation of that organism inside of someone. And so the opportunities for spread and for avoidance of the immune system, of vaccines, of medicines, is built in to these little reproduction machines. And so they are usually the pandemic causes, not always. For instance, the Black Death was caused by a bacteria. But recently, nearly all pandemics have been caused by viruses. And they, as I mentioned, with HIV, for instance, spill over into us from our environment, from all the organisms around us, all the time. It's a natural process. It's part of a biodiverse, interactive ecosystem where little slivers of nucleic acid move through hosts. And that's just going to continue, whether we like it or not. There's really nothing that we can do about that. And so if that process is built into our life in the ecosystem, then making us more packed in, more frequently exposed to those pieces of nucleic acid, sharing them more widely, more quickly, is just a numbers game. It's just going to increase the likelihood of global events.
In DNA sequencing, the speed of knowledge of improving understanding of things that were unimaginable a decade ago, but messenger RNA was known and being worked on, and that coupled with DNA helped us with COVID. Are you aware of any analogous techniques analogous to messenger RNA which could ride to the rescue in future epidemics?
Well, there's many other vaccine technologies. For instance, the adenovirus vector vaccines were DNA engineered. They were bits, they were the spike protein gene of SARS-CoV-2 spliced into an adenovirus DNA vector. So another virus was used to carry that sequence into vaccinees, and they would make an immune response. mRNA was around. We got lucky with that. And it's a technology that's not particularly new, and it remains to be seen how many other vaccines could be developed using that. It's certainly not a revelation, let's put it that way. We worked with the spike protein vaccine for SARS-CoV-2, but it's not going to protect us necessarily against others. The technology is not bad. What I would say is that however we make the vaccine, And the Chinese made the world's most common vaccine, which was just inactivated virus. They just took COVID and smushed it up and shot it into people, and that worked pretty well too. The main challenge now that I think we've all seen with some horror is, one, people are less interested in vaccines than they were, or at least they don't trust them anymore. And so the best vaccine, the most amazing technology to produce a new vaccine isn't going to do any good if we can't get a significant proportion of people vaccinated, one. And number two, the mRNA vaccines are fantastic. The rate at which they were developed, Operation Warp Speed, was undoubtedly a success. But I can tell you from practicing globally, on calls with Bangladesh, with Malawi, Taiwan, all across the world, they wanted the mRNA vaccine. Supplies never showed up because of international competition, because of the US and the wealthy European countries essentially putting dibs on the global production. It was not shared. And so that's the other factor, is vaccine hesitancy and global inequity in distribution. And so our technology is probably a minor factor out of all of that. Unless we fix those two things, it doesn't really matter how good our vaccines are.
Jumps of a virus from our relatives are very common, and it can also jump from an animal as far from us as a bat. So I just wanted to know, how far in the genome can a virus go?
Good question. We can be infected by an unbelievable array of viruses. We can even be infected by viruses of bacteria. So bacteria aren't even cells like our cells. They don't have an internal structure. They're very archaic. They're an ancient organism. And they have their own viruses. Viruses are specialized at reproducing in bacteria. And those viruses can infect us. They usually don't cause any disease, but we have lots of signals of those little bits of DNA traveling through us. One of the research projects that I'm involved with at Yale is the wastewater sampling, which a lot of you are probably familiar with from the pandemic, which we used as kind of a community sampling of the rise of infection in communities. And we have been looking at what's called metagenomics, which is basically all of the organisms present in a sample of wastewater, and trying to use that in an effective way. For instance, in monitoring these new infections that are starting to show up, can we use wastewater to surveil communities and detect, say, severe fever with thrombocytopenia virus as it shows up without having to get someone diagnosed in the hospital? And a sample of New Haven wastewater, and New Haven's what, a city of about 180,000 people in southern New England. It has one sewage treatment plant, so we can sample the whole population from one pipe coming out of New Haven. And it's basically just humans, because the sewers are closed in New Haven. There's no runoff, stormwater runoff. It's basically just us doing what we do to make wastewater. And in a sample of New Haven wastewater, there's about 40 million different organisms, different sequences coming out of us. Some of those are, things like corn, and because it's New Haven, opium poppy, chili pepper, So we're pooping that into the wastewater, and then we can detect, obviously, the DNA from that. But vast arrays of it are human pathogens. In a sample from November, we had every malaria parasite, human malaria parasite. We had lots of drug-resistant organisms. We had TB, particularly HIV. We had COVID. We had, trying to think of some of the sort of ones that made us sort of sit back and say, good heavens. And we had about 25% of those sequences completely unknown. So no hit in the database at all, had never been sequenced before. So a quarter of a daily production from 180,000 Homo sapiens in New Haven is at the current time unknown to science. So it just gives you a sense of our place and the passage of organisms through us, mostly insignificant, but obviously not always, because we are talking about pandemics and epidemics. And what the future is going to look like is what we've just been talking about. The change is very, very rapid.
How much greater is the mortality rate in countries that did not get access to the COVID vaccine as opposed to the countries that did? And is that moving through the population so there is an immunity now?
That's an interesting question, and it's impossible to answer. But what we did see was that Northern Europe and North America essentially had the highest mortality rates from COVID. And the probable reason is not because we're totally and utterly useless, and I don't want to give you the impression that I think that, but is most likely because of the age structure of human populations. So Africa, for instance, the average age of the whole of Africa is 18. And the massive majority of Africans are younger than that. So the impact of a virus like SARS-CoV-2 is going to be much, much less on a younger age population than it is on an older age population. So we had a very high peak of mortality in people over the age of 80, for instance. So your question perhaps could be asked, in the global rollout of vaccination, did the countries that rolled out targeted vaccination to the highest risk groups for severe mortality of COVID do better than those countries that didn't? And that is probably yes. We don't have great studies to look at that. But basically our original sin for our high mortality rates, and that includes the UK too. So although I was lauding the national health system, ultimately the UK did about as poorly at the beginning in terms of mortality and disease and death as the US did. The original sin was failure to get testing rolled out quickly enough, and then failure to use that to protect the highest risk populations, which we knew who they were straight away, were the elderly. And so essentially the majority of our morbidity and mortality was in nursing homes and assisted living facilities, acute elderly care settings where the death rate was way higher than anywhere else.
So COVID came from a bat. And my question, I had heard that scientists saw the virus developing in bats before it jumped to humans. So wildlife biologists are watching these things. And my question to you is, what is that dialogue like between your profession and those wildlife biologists? And how does that dialogue happen, and how do you evaluate that? I'm curious about that.
I mean, it's an interesting question. Again, I would say there's not any dialogue really, and I would point out, may shock you, but may not be a bad use of funding. The biggest US funded programs to do what you just described, which is monitor wild populations and look out for potential zoonotic spillovers, was just cancelled. Because, and there's, you know, it's not a black and white decision. It is probably impossible to find that spillover event like the 1920 bushmeat hunter in southeastern Cameroon that got infected with HIV. The first person to get COVID, to get infected with SARS-CoV-2, we have no idea. We think we know that it was someone from southern China who brought an animal to the wet market in Wuhan, or potentially a lab technician at the Wuhan Institute of Virology. We have no idea. But we do know that in villages around in Yunnan province, where a lot of these zoonotic spillovers take place in East Asia, you can find evidence of coronavirus infections in a large proportion of the villages. It happens all the time. These organisms travel through us. They usually don't amount to a pandemic, as I've already said. But the probability of a bat virus infecting a human is so high that it's not really the major factor in the risk of pandemic, because that is happening all the time. The real probability event is that infection being transmissible human to human, that person ends up in somewhere like Wuhan, that in Wuhan enough people get infected early on and then spread it beyond the city limits and internationally for a pandemic, and that then that process is able to continue. And that's not even guaranteed. So SARS-1, it was a more severe infection, and it did spread across 4 continents, but it didn't cause the COVID pandemic for a number of reasons. So there's a bunch of probabilities at each step of that process. But the spillover step is so common that it's probably not the right place for us to spend our time and money to look. I think that it would be fair to have some sort of surveillance for sure. But that very first event is likely inaccessible.
Hi. You had mentioned that Plaquenil was introduced. And I was wondering what the thought process was in introducing it and why it turned out to be a mistake.
That's a good question. If I could sort of describe our process and it was repeated in all the big academic medical centers across the US and likely beyond. We hunted in the data right at the beginning, knowing that this was going to turn into a pandemic. If we saw our first patient, and this was taking place in January and February 2020, what should we do? And we had a little bit of data from SARS-1 in 2002. We had a little bit of data from MERS, Middle Eastern Respiratory Syndrome, which is a camel to human zoonotic virus, but also some human to human, much more severe infection. And we sort of gathered together the literature and poked around in it and said, well, what could we do? And then there was an interesting debate between old doctors like me and young doctors like the people that produced that complicated algorithm that wanted to kind of control the situation. And the older doctors said, we don't really know, and the level of the evidence is exceptionally poor. So I don't think we should do anything until we have better evidence except supportive care. We should do those things that we know will be beneficial for the patient, but avoid doing things that we have no idea whether they'll be beneficial or harmful. But we were, as you can see, the minority voice in the room, and most centers made the same decision. We should do something. And so, interestingly, in that first week, when I was actually the ID consultant at the hospital in the week of March the 20, I think it was the 21st to the 25th, and we went from 4 COVID admissions to being full by Friday. So it went from Monday to Friday and just had exploded. And I admitted that week 2 elderly gentlemen with rheumatoid arthritis, both of whom were taking Plaquenil. And just doing a little back of the envelope calculation, it was clear that Plaquenil wasn't doing anything because they both got COVID and they were well overrepresented in the population that we'd just admitted. So, you know, these things evolve and we did a lot of other stupid stuff too. But for the best reasons, just not always for the best outcomes.
Sorry, putting aside the origins of COVID-19, of which there are many theories, I don't think anybody thinks that there were intentional agents involved in its spread. That said, it is possible when you engineer viruses to be like coronavirus or plague, you're working with bacteria, to have intentional agents, create things which could have tremendous negative impact on human biology. I would like to ask you how much technology you need to do that, because there are non-state agents out there that have to have been watching what's happened in the last 2 years and who aren't motivated like everybody in this room to minimizing the risks of repeats or adjusting environment to improve those risks. So I'm curious about, you know, is that in your field, is that a serious concern?
Do you want to leave refreshed and encouraged, or do you want to?
To date, everything hasn't been.
You want to go home miserable even more. There was a famous experiment not that long ago, I think it was 2012 or 2013, by a Dutch group in Amsterdam that took H5N1 influenza, which is avian flu. I mean, there's a pandemic right now in birds globally. Very occasionally, that bird virus, flu virus, will spill over. So it's probably a common event, but it's not a common infection. But when it does spill over, it causes an incredibly severe pneumonia and a very high mortality. I mean, we're talking 50% death rate with H5N1 infection. This Dutch group took H5N1 and infected ferrets who have a very similar airway to us repeatedly, and they passage that virus. It's called passage. It's just taking the what comes through one infection and then passing it back on to either the same host or another one. And after 5 cycles, they had an H5N1 that could transmit between ferrets, that had essentially the same cell surface receptors to infect the human airway. And that was, you know, could have been repeated, that experiment, and it's common knowledge, so, you know, there's not much security around that information, pretty much anywhere. Now, could that be a potential bioweapon? I guess. I mean, there's tons of other considerations. I mean, just shaking that sample of ferret-adapted H5N1 out of your trouser leg at JFK isn't guaranteed that a global pandemic will result. There's lots of other factors that would go into the dose of exposure and how you got the right person, and, you know, whether they would be asymptomatic for long enough to infect a number of other people, or whether the infection would be too severe, like Ebola, where the pandemic potential is extremely limited. So, although it sounds easy, the practice is highly speculative.
But to be clear, the creation in a lab is a low tech.
Yeah, even.
I'm not talking about spreading.
Yeah, no.
Maybe you start in Kinshasa.
The creation is now low tech, and even splicing and making new organisms with moving genes and splicing them into a specific position in the genome is something that you could almost do with a chemistry set in your bedroom.
Easier than making drugs.
Probably not easier than that.